Today, we are going to take another look at this partially filled hemispherical bowl, and we are going to once again calculate the volume of the water that's in the bowl. So, if you would recall, this is still a question for multiplication, in which one of the factors is variable. We're going to calculate volume as the cross-sectional area multiplied by the height. So what we're going to use is that volume is cross-sectional area multiplied by height. Because what we notice is if I look at this slice of water, this orange slice of water, if I look at this bowl from the top, that shape will always be a circle. Anywhere we cut horizontally along this bowl, we will see a circle of water. So it will always have the same shape, but the area will change. Down here at the bottom of the bowl, we see this little small circle, and up here at the surface of the water, we see a much larger circle. And what we care about is, since it's a circle, all we care about in a circle is the radius, unless we're defining a very important constant, in which case we use the diameter. Thanks, ancient Greece. You really messed that one up for us in the future. So our volume of this little slice is going to be pi r squared multiplied by the height, which is the part that's going to get thinner. So I refer to that as the delta variable. So this is the change in height. Now we just need to define h. We have to decide where h goes, and then find a relationship to write r in terms of h. So once we've established what we're going to do, area of the circle multiplied by the height, once we've established the delta variable, now we need to write all the other variables in terms of the delta variable. And what we notice here is that we have to decide where h goes. So now we have to finish defining h to make sure it goes in this vertical direction. So now we need to define h, and it has to be vertical. So h has to be somewhere of vertical distance involving the slice. And then we have to write everything in terms of the delta variable. In this case, that means r. Write r in terms of h. So we need to define where we're going to put h, and then we need to define, write r in terms of h. Yesterday, what we did was we defined h to be this vertical leg of the triangle. So h was the distance from, h was the distance from the top of the bowl down to the slice. So yesterday, we defined that value of h. What that allows us to do is to pull out that triangle and get a relationship between h and r, write r in terms of h, and have a function that we can integrate. The other thing that this does is define where 0 is. Once we define our delta variable, one end is the slice, the other end is 0. So that forces us to say that 0 is up here at the top of the bowl. So this means h equals 0 is at the top of the bowl. So now H equals 0 is at the top of the bowl. The water starts at H equals 3. And the water ends at the bottom of the bowl at H equals 8. So we got to choose where we put H. And that told us where 0 was. That told us what the positive direction is. And so now that's part of the problem. Once we decide that that's where H is going to go, that forces us to assign where 0 is. That's what informs us where 0 is. Or we could choose where 0 is and then define H accordingly. So this affects how we write the relationship between H and R. So now with H defined this way, I have a nice easy way to get a relationship between H and R. In that right triangle, the hypotenuse is 8 because it's the radius of the circle. So I get H squared plus R squared is equal to 8 squared. And so I can write R in terms of H. So R is the square root of 64 minus H squared. Now I can set up my integral. So the volume of the slice is pi times the radius, which is square root of 64 minus H squared, because it's pi R squared, times the delta variable, which is delta H. Now I just need to add up all such slices into a Riemann sum, and then out the other side will come our integral. So once we set up the volume of the slice, we can see what we're going to be integrating. I'm going to factor out a pi. And I'm going to simplify the square root of 64 minus H squared squared to just be 64 minus H squared. And in the continuous, the discrete delta H in the definite integral will be a continuous dH. But now we have to integrate where we have water. And once we decided that H was going to be the distance from the top of the bowl to the slice, H equals 0 is at the top of the bowl, and there's no water between H equals 0 and H equals 3. So our integral, the 5 centimeters of water that we want to integrate, is from 3 to 8, not from 0 to 5. 0 to 5 is the top part of the bowl, but the water is in the bottom part of the bowl because gravity. So we're going to integrate H equals 3 to H equals 8. This is an integral that we could easily calculate by hand, but heck, isn't this why we have the calculator? So we have pi math 9 of 64 minus H squared with respect to H from 3 to 8. So 497 points. I usually say 5 significant figures. So we'll have this as 497.42, let's call it. And it's a volume, so it'll be cubic centimeters. Cubic centimeters make sense because the 64 minus h squared, this comes from the pi r squared. So that's square centimeters because it's an area. And delta h is also in centimeters. So I have square centimeters times centimeters. So it works out to centimeters cubed. So this is the area in square centimeters. The dh is in centimeters. So it makes sense that we'll have a result in cubic centimeters. I suppose I should have gone back one more level and say that r is in centimeters. And so that when we square it, it's in centimeters. So if I was properly color matching things, the cm would be in purple and the 2 would be in green, but I didn't, so.
Professor, on the V slice line, how come we squared it?
The area of the circle is pi r squared.
Oh, got it.
This
Thank
circle
you.
up here.
Got it.
So this is how we approach the problem when we define h from the distance from the top of the bowl to the slice. So now we have to, that's where we made a choice to let h be the distance from the top of the bowl to the slice. That was our choice. So let's go and make a different choice. Let's get ourselves another hemispherical bowl. Make sure we mark our center. Oops. Hands are a little wobbly. Don't know if that's a more coffee problem or a less coffee problem, but as usual, I know what solution I'm going to apply. So, same hemispherical bowl. If I look at this from the top, it'd be a circle. And we still have the same 8 centimeters radius. And we still have the same 5 centimeters depth. And I'll go to the nearest 10th to make all the Mustang fans happy. Unless you got your Mustang in the wrong year, in which case it's like a 4.6. It's 4.6, right? Anyway. So, so this part of the setup is the same. This is still a circle, so I still need the radius of, in cross section, this is still a circle, so I still need the radius. And I still need to get a relationship between r, and I still need to turn this r into a vertical variable, so I still need this right triangle. And the hypotenuse of this right triangle is still 8.0, which is more of a Mopar size engine. I don't think they ever made an 8-liter. I think Cadillac made an 8-liter. You can correct me in the comments. I think Cadillac made an 8-liter and it made like 170 horsepower. It's hilarious. So now we need to define an h. The same, everything is the same. We need to define an h, and I'm going to use a different h this time. So I'm going to use a capital H. So I'm going to shout this problem at you. We still have the same volume of the slice. Volume of the slice is still pi r squared times our delta variable, in this case, delta H. We still need to define a value for H and then write R in terms of H. So I'm going to make a different choice this time. Last time I said H was the distance from the top of the bowl to the slice. This time I'm going to say H is the distance from the bottom of the bowl to the slice. So I'm going to let H be the distance from the bottom of the bowl to the slice, because we're changing things up. Let H equal the distance from the bottom of the bowl to the slice. Once we make that decision, first step is to stop having regrets about the choice that we made. It's the choice that we made, let's move forward with it. But this choice tells us where H equals 0 is going to be. Since the H is the distance from the bottom of the bowl to the slice, 0 is at the bottom of the bowl. And up is positive in this case. So we've made, this is the result of our choice. This is the consequence of choosing H to be this distance. The water, so the water starts at 0, so H equals 0, is the bottom of the bowl now. The water, the top, the surface of the water is at 5, because it's 5 centimeters deep. And H equals 8 is the top of the bowl. Oops. When we look at the triangle, I can't use H in the little triangle that I have up here. So now this is going to change our relationship between H and R. Because now in this triangle, H is the distance from the bottom of the bowl to the slice. The vertical leg of the triangle is the distance from the top of the bowl to the slice. So I can't call it H. H is spoken for. It's this distance. So H, this distance, all right, the vertical leg of the triangle is now 8 minus H. Because if the distance from the bottom of the bowl to the slice is H, and the distance from the top of the bowl to the slice is the leg that we're interested in, and the distance from the top to the bottom of the bowl is 8, then the leg we're interested in is 8 minus H. And now I'm extra regretting making the radius of the bowl 8 and using H as the variable. Dang it, English. I shouldn't blame English. I have only myself to blame. Yes, I should say H. All right. So now if I use, when I write the Pythagorean theorem, I have 8 minus H squared plus R squared is equal to 8 squared. And so R is the square roots of 64 minus 8 minus H squared. So I've changed where I've defined my variable. So I'm going to change where I'm integrating, but that's also going to change the function. So now the volume of the slice is pi times the radius squared, and the radius is 64, or the square root, excuse me, the square roots of 64 minus 8 minus h squared times the delta variable, delta h. Now, to the horror of other calculus teachers, I'm just going to say, instead of writing the Riemann sum, I'm just going to write the words Riemann sum. Because what we're really interested in is getting the definite integral. And the definite integral, I'm going to factor out the pi just like I did before. I'm going to simplify 64, the square roots of this stuff squared, and just get 64 minus 8 minus h squared. Our discrete delta h becomes the continuous dh. And now, instead of integrating from 3 to 5, we integrate where the slices where there's water. 0 is at the bottom of the bowl where there's water, and the water ends at 5. So we'll integrate from 0 to 5. And now the big test to see if this works. So I'm going to integrate pi, math 9, and the function is 64 minus 8 minus h squared with respect to h from 0 to 5. Same thing, 497.42. Cubic centimeters. So this is great. We have a choice of where we could put the variable. This is horrible. We have a choice where we can put the variable. Moreover, we're not limited in our choices. We have an uncountable infinity of places to put our variable. I've only done 2 because I got uppercase and lowercase h, so I just did 2. And there are really only 3 reasonable places to put h. Top of the bowl, bottom of the bowl, maybe the surface of the water. It would be weird to say, let h be the distance from 10 meters above the surface of the water to the slice. That would be that's just weird. But like I said, we have a lot of different places that we could put the h. So without redrawing the whole picture, I could say let h, I'm going to use a different one. Let's let, I can't think of another word for height. Oh, I'm going to say, no, I'm not going to use d. That's terrible. I was going to use d for depth of slice. I'm just going to use z because z is cool. So let's let z be the distance. Here's where I'm picking a different 0. Distance from the surface of the water to the slice. So h equals 0 is the surface of the water. Oh, sorry, z equals 0. I know, buddy. Like, I should be drawing a picture for this, shouldn't I? My dog doesn't like it when I don't use the visual assistants. But, you know, I'm running out of space here. Dude, I'm running out of space. He's looking at me like he doesn't believe me. Z equals 5 is the bottom of the bowl. And the top of the bowl, although we don't need it, is at -3. Now he's really giving me a look. He's like, oh, dude, there shouldn't be negative numbers. Dogs are not into negative numbers. They can count, but they don't know how to do fractions. That's what I've discovered about dogs and their relationship with math. So Z equals 0 is the surface of the water. Z equals 5 is the bottom of the bowl. The positive direction is down. So we're going to integrate from 0 to 5 again. But now the leg of this, the vertical leg of the triangle, if I just pull out the right triangle, the water is cutting through this triangle at some point. And the slice is down here. Oops, although the slice should end there. Here's still the radius. Get the water back in there. Now my Z is the distance from the surface of the water to the slice. But I still need this leg up here. Since the surface of the water is at Z equals 0, and the top of the bowl is at Z equals -3, the distance from the surface of the water to the top of the bowl is 3. So the vertical leg of the triangle is Z plus 3. Great, I needed to pick, I had a problem with 8 and H sounding so similar, and then what do I pick for this one? Z, so it'll sound like 3. If you had a professional teacher, things like this wouldn't happen because they'd work from a script or something like that, but y'all are stuck with me, so. So the distance that we're interested in is Z plus 3. This changes what we write for the radius. The radius is now the square root of 64 minus Z plus 3 squared. And our integral will go from 0 to 5 again, but from the surface down to the bottom of the bowl rather than the bottom of the bowl to the surface. So let's see, the integral of math 9, oh, that's the integral part, of 64 minus Z plus 3 squared with respect to Z from 0 to 5. That's the other 0 to 5. That's from surface to bottom, whereas the 0 to 5 in the previous one was from the bottom to the surface. Let's see if I did this right. And we get the same thing, 497.42. So good news. Good news, everybody. Or is it good news, everyone? Good news, everyone. We have a choice of where we could put our variable. Bad news, everyone. We have to choose where we put our variable. The good part of the bad news is you can't mess it up as long as you're consistent. You can literally put your variable anywhere. Just respect your choices and accept the consequences of your choice. If we choose H, if we want the convenient parts to be in writing R in terms of H, then we can choose H to be the distance from the top of the bowl to the slice. That makes this expression smaller, but then we have to live with the consequence of integrating from 3 to 5 instead of from 0 to 5. If we want to integrate from 0 to 5, we're going to have to deal with a more complicated expression for the radius. All choices have consequences. Welcome to Mass Effect 4, Calculus Edition. I'm just kidding. The consequences don't really matter. It's just that the screen will flash red or green or blue after we click accept. You know what I mean? All right. Well, that's going to do it for today. Today was about the choices that we can make in defining our variables. The process that we've been going through is the important thing. It's important to look at this in terms of the process and not just look for forms that you can kind of plug things into. So don't just go on autopilot and integrate from 0 to 8 or from 0 to 5. Look at the reasons that we're making these choices so that we can learn to read what the definite integral is telling us. All right, now that's actually going to do it for today. We'll see you all on tomorrow. Everybody have a good day, and thanks for playing.